Welcome everybody. This is part 2 of the CUDA to SYCL migration workshop. So just a recap of what is the agenda. This is a 3-part series. So last month we had a session on introduction to SYCLomatic Tool, and we learned how to compile and execute SYCL code on Intel Dev Cloud. We looked at 2 simple examples. And in today's session, March 15, so we will be looking at more complex CUDA sources and how to migrate that to SYCL and then compile it on different CPUs and GPUs. And then finally, we have in April next month, we have another part 3 of this series. Mainly, this is a session where you as audience can come with any CUDA source that you're working on. If you want help with migrating to SYCL, we will work out any issues, and we will also look at any other tips and tricks for using SYCLomatic and limitation, and learn about, answer any final questions about migrating from CUDA to SYCL. So with that, session 1 was last month, and then in today's session, so this is the agenda for today. So we will be migrating a more complex CUDA source with the SYCLomatic tool, and we will also learn how to migrate the kernel code with SYCL features. So mainly, the last week's example we used were simple CUDA examples. In this week's session, we will look at CUDA code, which has more CUDA features like local memory, cooperative groups, work primitives, or atomic operations. So we will try to migrate this type of code and then see what the results are and what are some of the things you need to do to successfully complete the migration, right? And again, session 3, like I said, will be like a mini hackathon and also a Q&A session where we will share some tips and tricks and limitations of SYCLomatic tool. So just a reminder, so the prerequisites for this workshop is that we had asked you to bring a CUDA development machine or have access to a CUDA development machine that which we will use to install the SYCLomatic tool and migrate the code. So this is just to run the tool, just one command line. And once the migration is done, we will be taking that code into Intel Dev Cloud environment where we have a bunch of CPUs and GPUs that we can test the SYCL code, right? So we will complete any migration on the Intel Dev Cloud. So even if you don't have a CUDA development machine accessible, so you can just follow the demo that I do, and then you can continue with the second part, which is mainly trying to compile and run the SYCL code on Intel Dev Cloud. Right, so the workshop overview, just like I mentioned, mainly involves 2 steps. First step is migrating CUDA source to SYCL on the CUDA development machine, and part 2 will be taking the migrated SYCL code and then running on Intel CPUs and GPUs on the Intel Dev Cloud. So with that, let me get started. So I think these were all just slides, just a reminder of the workflow that we will be doing. So we would start with the CUDA code. We will use SYCLomatic tool to migrate it, which will result in C++ with SYCL code. We'll inspect the code, and then finally we will build it so that now the code that was just running on Nvidia GPU will now run on any CPU, GPU, FPGA from any vendor, right? So that's the main goal of this workshop. So with that, I will get started. I'll spend about 10 minutes to do a quick recap of what I did last month, mainly go over the steps to install SYCLomatic on CUDA development machines. So if anyone did not attend the previous session, they can still follow along and get started with today's session. So with that, I will jump to my CUDA development machine. So you can do the same thing. just get access to your CUDA development machine. So I've already logged in here. So let me do some basic sanity check to make sure that my CUDA development machine is set up correctly. So the command that I use is Nvidia SMI. So this is just to make sure that CUDA is installed. So you can see that the Nvidia driver version is displayed. CUDA version 11.7 is installed on this system. And you can see that the Nvidia card that I have is the Tesla P100, right? So as long as you see an output for Nvidia SMI, then this shows that the CUDA system is set up correctly and they can proceed with the next step, right? Another thing is the CUDA installation path, right? So by default, it is installed in, I think, user local CUDA, right? So this is the path. So you should have something in there, and /include is where all the header files are. So just make sure that you have these header files in the actual CUDA installation path. So if you have installed CUDA in a standard, non-default path, then just make a note of the directory where it's installed. So we will need that later when we start the migration, right? So this is one check we usually do. And finally, make sure that you have, you can compile CUDA code just using the Nvidia tool. So if you have NVCC -- version, so this is another check just to make sure that CUDA is correctly installed. So if you have these three checks complete, then I think we are good to proceed with the next step. So the first thing we will do is download the SYCLomatic tool. So I had showed this last month, so we will quickly do that again. So if you've installed it last month, you can also delete it and then install the latest version, because we have a build that is created every day. So that's what we will be doing. So where do we get the SYCLomatic tool? So if you just Google for SYCLomatic, then the very first link you get will be a GitHub link, right? So we will open the GitHub for SYCLomatic. So this is completely open source, and we have the source here, and we also build the tool every day. So if you click on tags and releases, you can see that every day there is a build being created. Right? So if you see, so we can use today's build, 15th March, and under assets, you will see that there are a bunch of files here. So we will be installing the Linux release. So what we'll do is just right click on this Linux release.tgz and then copy the link address, right? So before that, let me paste this GitHub website on the chat window so that you can access this one. Right, so you can copy the build here. So let me go ahead and then copy the Linux release zip file. So I do copy link address. So once you've copied, so you can go back to your CUDA machine. And what we will do is create a folder called SYCLomatic, and then we will copy the zip file there, right? So I'll do a mkdir SYCLomatic, and then cd. Right, so here what I'll do is I'll just do a wget and then paste the link from GitHub that I just copied. So if you do that, it should copy the SYCLomatic tool. So it's only 23 megabytes. So when I say install SYCLomatic, we're not really installing or running any script. All we are doing is just unpacking the zip file, right? And we will be accessing the binaries directly. So that's what we will be doing. So once we've copied the zip file, so we will use tar to uncompress this one. So just do tar minus xvf, specify the file here, and this should unzip all the files. So if you look at the files here, you can see that it's created a bin folder an include folder, lib folder, right? So this is all the tools for SYCLomatic. So all the binaries that's needed for the tool is in the bin folder here. So if I check on the bin folder, you'll see that there are some executables called C2S, DPCT, intercept code. So C2S is the main binary we will be using to migrate CUDA code to SYCL. So we will be accessing this directory path when we are migrating. So it's a good idea to add this bin path to export this to your path, right? So I will do that so that it's easier. So export equal to right. So and then I will copy the. So this will be different, you know, on your computer. So make sure that you're copying the path where you just installed SYCLomatic, right? So I'll just add this path. And then now you should be able to just directly access the binary. So you just do C2S -- version, right? And then they should display the version. So DPCT was the name of the tool previously. So that's why we see DPCT version 16. So as long as you get this output when you do C2S -- version, that means your installation is all good and we can proceed with migration. So let me know if you have any questions. Feel free to unmute and then ask a question, or if chat is more convenient, you can also type your questions in chat. So hopefully people are able to you know, install SYCLomatic and they are seeing this output here, right? So let me quickly check if there's any questions so far. Okay, so once you're at this point, so now we are all set to start to migrate CUDA code to SYCL. So let's start with a very basic example that we did last time, just one very simple CUDA source, so that this will just be like a recap. So there is a test code available. So let me paste that code in the chat window. Okay, so if you open this link, we have a test code, a very simple CUDA source here. So you can see that we are including CUDA.h, and then this code is very small code. So all we are doing is we're initializing 3 arrays, A, B, and C, and we've initialized it to some value. And then we are allocating memory on the GPU, Nvidia GPU, using CUDA malloc. And then we are copying A and B to the device. And then we are submitting a kernel called vector add, which essentially does C equal to A plus B. And then we copy back the memory from Nvidia GPU back to the host, and then we print the output, right? And then we free the allocation. So it's as simple as a very basic CUDA code can get. And you can see the kernel function here. Mainly it iterates over all the thread index and then calculates C equal to A plus B. So let me just okay. Looks like there is some Zoom issue, so let me know if you're still experiencing this. Anyway, so this is the code that we will be migrating to get started with. So let me go back to my Nvidia system here. So I've copied this code in one of the directories here. So you can see that I have my test.cu file here. So if you open the test.cu file, it should be the same file that we just reviewed. So we will be migrating this to SYCL. So let's, so how do we migrate this to SYCL? So it's a very simple command. So the main binary for SYCLomatic tool is C2S, right? And then you just specify the CUDA file. test.cu, right? So if you just hit enter, so you can see that printed out some information. So what it actually did was it created a directory called dpct_output, and that's where the migrated source will be stored, right? So if you, let's check the directory here, you can see that there is a new folder created called dpct.output. So if you go into this dpct output, you will see that there is a test file. So instead of test.cu, it created a file called test.dp.cpp, right? So let's look at what's inside of this test file. And if you look closely, you can see that instead of having including the CUDA header file, now it's including the SYCL header file, and there's also a helper file that's been included. And then if you actually inspect the code, you can see that all the CUDA APIs have been migrated to SYCL APIs, right? So we have, instead of using CUDA malloc, it is now using the SYCL malloc_device, which essentially does the same thing, allocates memory on the device, and we use memcopy method to copy, and then the actual kernel is submitted using this parallel for construct, right? And again, we copy back the memory here. We copy back the memory, and then we free the allocation using SYCL free. And at the very top, there is the kernel function. You can see that instead of using the threading index in case of CUDA, instead of that, we are actually using this get local ID, right? So that's how it executes each one of these computation on a different thread, right? So this is just a recap of what we did in the first 10 minutes of last month's session. So mainly installing SYCLomatic and then showing a very simple source, that CUDA source, and then migrating it to SYCL, right? So if you want to compile this one, so the easiest way is, like, since it is migrated to SYCL, now you can take the source to another machine which has like Intel CPU or GPU, or you can take it to Intel Dev Cloud and then compile it there, right? So you do need to install the SYCL compiler, which you may not have installed, but if you want to install the SYCL compiler, there are instructions. You can download the One API based toolkit, which will give you the SYCL compiler, and you can use that to compile this source, right? So if you want to quickly check, so I have installed the SYCL compiler here. So let me just show you that this code that we just generated actually compiles. So we just use ICPX, that's the compiler. We use the SYCL flag, and then we can specify the test file. And if you run this, this should actually compile and then give us an output. You can see that there are some warnings here, which we can ignore for now. And you can see that the output was created. And then if you run the code, you can see that the output is printed out. So maybe computed that 2 + 1 is equal to 3. So this is the entire workflow for migrating CUDA source to SYCL. So with that, we will get started with today's session, right? So this was just a simple CUDA source. So now we will look at migrating a more complex CUDA source. So just like last month, we were getting the CUDA examples from Nvidia samples repository, right? So we will do the same thing. So let me try to find that repo here. Okay. So mainly we will be accessing this repository, Nvidia CUDA samples. So let me paste that in the chat window here. Right, so you will have to clone this repo into your CUDA development machine. So go ahead and copy this Git link, and then we'll do a Git clone, and so that we have all the samples. Right, so if you let me go to my CUDA machine again, and mainly what you will be doing here is just do a git clone and then enter the Nvidia repo git link, right? So I have already cloned this repo, and this should actually clone, and then it will give you a directory called CUDA-samples, right? So hopefully you're able to clone. So this should not take a long time. So it should be done in a few seconds. And once you've done that, if you go into CUDA samples, and then there's another folder called samples. If you look under samples, there are various directories. So this example that we will be migrating is actually in the third folder, which is 3_CUDA features. So let's go into 3 CUDA features, and then you can see that there are various examples here. So we will be looking at this example called Jacobi CUDA graphs, right? So let's go into this directory, CUDA graphs directory. So hopefully you're able to access this folder, and inside this folder you can see that there is a CUDA source, right? And also along with that, you can see that there's a main.cpp file, and there's also a make file, right, to compile and check this output. So if we quickly want to look at the main file here, you can see that mainly this is using the CUDA runtime header file, and then it's also using some helper CUDA files, and then helper_timer, and then it's also using the Jacobi.h file, right? So all these dependencies should be available here, right? So we have CUDA Jacobi.cu, we have Jacobi.h, and then we have the main.cpp. So those 3 are the 3 source files. And then it's also using some common files, which are in the directory called common thing. So if you look under here, we went into samples folder, and there's also a folder called common folder. And then here there are a bunch of these helper_CUDA, which was used, helper_timer, which was also used, right? So we will be, I'm just showing the directory structure. So we will be using these paths to actually compile and also to migrate the files, right? So in the previous example that we looked at, it was just one single CUDA source. But in this example, we are using multiple files. So we will be using slightly different approach. So let me go back into the samples Jacobi example folder, right? So usually if you have multiple source files, so instead of migrating each file one by one, we can actually build a list of files that this project is using, and then use just one command line to migrate all the files, right? So the way we do that is we use this tool. Since there is a make file, we will use this tool called intercept code. So if you call this binary, so this binary was actually installed with the SYCLomatic tool in the bin folder. We'll call this file and then just type in make, right? So this will run some command and generate a JSON file. So let's look at the directory here. So you can see that it just created this JSON file called compile_commands.json, right? So let's look at what's inside that. So if you look at that, it just gives you a list of files that this project is using. You can see that it's using the Jacobi.cu, it's using the main.cpp, right? So this just builds a list of files that need to be migrated, and this is what we will use as input to do the migration. Yeah, I think there's a question whether you can use CMake. So you first have to, so CMake will usually will generate a make file, right? So you'll have to create the make file and then use the make command. Okay. So hopefully you're able to run this command and then generate this compile commands.json. So once you've done that, the next step is mainly to run the SYCLomatic tool to migrate the source, right? So for that, we'll be using a bunch of command line options. So let me type in the command. I'll also paste this in the chat window so you can. Okay, so here's the command we will be running to do the migration, right? So let me paste this in the chat window and then I'll explain what exactly we are doing. All right, so I've just pasted the command to do the migration. So before I hit enter, so let's review what we've done here, right? So C2S is the main binary, and then we are using -p option to mainly pass in this compile commands JSON file. So this is how the tool will know what are all the files that need to be migrated. And then we are also using this command line option called inroot, and then specifying the path where the common files, where all the support files are located. So we have to go like 3 directories behind, right? So once we are in the root directory here, that's when the common files and the sample files both are available. So we're just pointing it so that it doesn't just compile, it doesn't just migrate the source files that you see here, the 3 source files, but it also migrates all the common files, right? And then we are using this new flag, right? So which is it's saying use experimental features equal logical group. So this is mainly this specific CUDA example is using some new features like cooperative groups. So mainly the support for it right now is was just recently added as experimental features. So that's why we are adding this new. Usually for other examples, you won't need it unless unless the CUDA example is actually using cooperative groups, right? And then finally, we are using another option called the use custom helper equal to API. So this is mainly when the SYCL code is generated, it uses some helper functions. So all those helper functions will also be added as output. Right? So those are the options. So so the details of this command line is available in the documentation, which I will share later. So mainly, if we run this command line, you will see that it will process the files, and then mainly, again, it creates a folder called dpct_output, right? So don't worry about the warnings and errors that it has generated, so we can look at those later. So if we just list all the files here, we can see that it just created a folder called dpct_output, right? So if we go inside dpct_output, we will see that there are 3 different folders. One is the common folder that it copied over, right? There's also an include folder that it created, and also a samples folder. So if we look inside of samples, you'll see that it's just directories, and then you will see that the 3 CUDA source files is now migrated to .cpp files here, right? So these are the migrated files. So and then if you go back to the common folder, you will see that there were a lot more common files in the original folder, but in the output folder, it just copies the output, the header files, which are actually used for this project, right? And these are also migrated to SYCL. If there's any CUDA calls within these headers, then these are also migrated. And the next one is that, so we looked at common folder, we looked at samples folder, and there's also an include folder. So if you look at the include folder, you will see that there is a folder called dpct. And then you can see that there are some helper files, right? There are some atomic.hpp. So these are all SYCL helper files, right? So when the tool migrates to SYCL, it's using some wrappers to make the migration easier. So that's all. These are all the files that are generated, right? So at this point, once you have this output generated in your dpct folder, so now the job of migration is done, right? The SYCLomatic tool is done. The next step is we have to take this source over to Intel Dev Cloud, and then we will start. We'll try to compile and see whether we can even compile this migrated code, right? So that's the next step. So this is all you need on the CUDA development machine, right? So all you need is install the SYCLomatic tool, run one command, or if you're using makefiles, you run the intercept build makefile, and then you run the main tool command, and which will generate this directory of files, right? So once this is done, we will take this over to Intel Dev Cloud and then try to compile it. So I think I don't think we can copy text from chat. Is this not? Are you not able to select this one? So I'm able to select this one. Okay, so I guess you cannot copy this one. Yeah, I noticed that even I can select it, but I don't think you can copy this one. I will share another link. Where,
hold on 1 second, and I'll make you a co-host.
Okay.
Okay, try again.
No, I think I'm able to copy. I think the audience is not able to copy and then paste it into their terminal. So I can share a different
link. I see.
Yeah. No, I have all these commands in Jupyter notebooks, so I will share this. Okay. So with that, I think we are done with everything we need to do in the CUDA development machine. So now we will go to part 2 of this workshop, which is mainly we will take this migrated code and we will compile it on Intel Dev Cloud, right? So for that, we will be accessing the Intel Dev Cloud. So hopefully everybody has a Dev Cloud account signed up. So the website for this is devcloud.intel.com/oneAPI. So if you access this link, so you can sign in to Dev Cloud, and then it should say that you're signed in on the top right corner. So once you're there, we will access the Jupyter Notebooks interface of Dev Cloud. So Dev Cloud is mainly a cloud cluster that we have. And we have a bunch of Intel CPUs and GPUs that you can access to run your test code. So it's signing up for this one is free. So you will get access for 120 days, and you will access to all the oneAPI tools, and then also access to all the latest Intel GPUs and CPUs. Okay? So the way to access this one, there are mainly 2 methods to access Dev Cloud. One is you can just do an SSH and access through command line, or the second one is we can access using Jupyter Labs interface. So Jupyter Labs is what we will be using because we have some training content that's written in Jupyter. So to access that, once you've logged in, click on Get Started, and at the very bottom, you will see Launch Jupyter Lab, right? So go ahead and then click on this option that says Launch Jupyter Lab, and this should, in a few seconds, should open up an interface that looks like this, which is the Jupyter Lab interface. So I'll give you a few seconds here to catch up. So let me check if there's any more questions. Okay, so once you have this interface open, so what we will do is we will go to File menu and say New, and then launch a new terminal, right? So this should open up a terminal within your Jupyter interface, which will look like this. So it should open up a terminal window, and then here you can access the Dev Cloud systems, right? So hopefully people are at this point here. So what we will do, the next step is mainly download the latest training material to your local folder. So the list on the left that you see is mainly all the pre-populated training content for various Intel tools and compilers, right? So we will be copying the CUDA to SYCL migration to the home folder. So the way we do it is we will copy one API workshop for SYCL migration, and then copy it to your current path. So by default, if you open up your terminal in Jupyter and then run this command, so this will just copy the training material into your home folder here on the left-hand side. So let me paste this command in the chat window. Right, so if you run this command, so this should have copied a folder called CUDA to SYCL migration. So on the left-hand side, so you should see a folder called CUDA to SYCL migration. So if you click on that folder, you will see 5 different modules here, 5 different folders, which starts off with like introduction. So this is all the information that I went over in the first 15 minutes of this presentation. So all the command line instructions that you need to install the tool and to set up your tool is all available in this one. So the way you access this material is there is a welcome file here. So if you click on the welcome file, it has some information, and then we have links to the different modules, right? Starting with the introduction. So if you click on introduction, this just talks about just the motivation behind migrating to SYCL. Why do we need to do this one? Just giving you some background about CUDA versus SYCL, program structure, how the execution model works with CUDA versus SYCL, and also information about the tool, right? So how the tool works, and then it has all the instructions for accessing how to do a sanity check. This is all the same stuff that I did earlier in the presentation, right? To run your Nvidia SMI, how to install the SYCLomatic tool, right? So this is just for your reference. If you want to, if you're not following around currently, you can use this notebook to actually learn how to do it and then do it on your free time. Okay. Right. So in last month's workshop, we actually did migration for simple vector add, and also we did migration for sorting networks. Right. So in today's workshop, we will mainly be doing the accessing the third workshop content here. So the one that says SYCL migration Jacobi Iterative. So you can see that when you access this folder, there is a Jupyter notebook file here. So if you open that, this will give you all the steps that's needed to do the migration, starting with installing the SYCLomatic tool on your CUDA development machine. It will show you all the different commands you need to run. So you can see that I have the same instruction that I gave you now. We have it documented here, so you can try this later. So we clone the repository, access this folder, and it gives you an overview of all the files that are there that we are migrating. And then we install the SYCLomatic tool, right? And then we run the command to migrate the code. So we just did this. We did the make clean, we did intercept build make, and then we also ran the actual SYCLomatic tool, which was mainly we specified the path where the JSON file is. We also specified a special option called use experimental feature logical group. We run this command line. This is what will generate the output for you. And this document also explains what each one of those command line features are doing, right? So once we've migrated, we will look at the output file here. So before that, let me check for, okay, any questions? Okay. So in the same folder, you will see that we have a folder called dpct_output. So this is the output of SYCLomatic that was just generated. So you can either copy your own a folder that you migrated on your CUDA development machine. You can copy that and then drag and drop it into your dev cloud interface here, or for people who did not have access to the CUDA development machine, we already created the SYCLomatic output here along with the documentation, so you can directly start accessing this folder here. So if you look at the dpct output, you will see that it has 3 different folders. A common file, these are the common CUDA files that are used for the project. Sample, this is the folder where we have the actual source, right? So let's go into the source. So if you go into the source folder here, you'll see that there are 3 files that are added here, 2 C++ file. So these are the CUDA to SYCL migrated files, right? So if you scroll down, you'll see that instead of including the CUDA.h file, it's actually including SYCL header files, right? And it's also including this dpct header file, and this header file is also included in the output. So if we go back to the output folder here, so we have an include folder here, and include folder has this dpct/dpct/http, right? So these are all the files that are needed to compile. And then the rest of the code, I mean, it's using the CUDA helper files, and then it's also using just the C++ header files that are included. And if you look at this main code here, right? So if you start looking at the commands here, so you can see that there are some warnings that are being generated by the SYCLomatic tool. So mainly the things that there may be an issue with the code that's being generated, so it will generate some error messages here. So what we can do is analyze this one. You can see that in the original CUDA source, we had a malloc, CUDA malloc, so that is being migrated to CUDA malloc host is being migrated to malloc host, and then other SYCL calls. You can see that we are creating a queue. We have malloc_device, so this is mainly migrated from CUDA malloc API, right? So you will see that this file actually, instead of having CUDA APIs, it has SYCL APIs, right? What we can do is we can start off by just trying to compile the migrated code, and then we'll start, we'll see if it compiles or not, and then we will start resolving any issues that we see here, right? So to get started, if we will go back to the command line interface, and then we will go into this directory, CUDA to SYCL migration, and then we'll access the third module, which is the Jacobi Iterative, and we will access the dpct folder. This is the folder that has all the migrated source files, and then we go into the samples, samples, CUDA features, and then Jacobi files, right? So this is where we have the source files. So you can see that there are the 3 source files here. So we will compile this migrated code to see whether it even compiles or not, right? So the command to compile is icpx SYCL. I think we have to include the support files here. So let's include the common folder, and also we will include the include file, and then we will compile all the star.cpp files that are in the current directory, which are these 3 files here. And I'm thinking, what else do we need? we will just ignore any warnings for now, and then see the output, right? So usually, the tool does not migrate 100%, so we might see some errors, right? So you can see that there are a bunch of compile errors, right? So we'll have to analyze one by one and then see why this particular code did not migrate completely, right? So if you look at the first few errors, it's saying that CUDA graph underscore T, unknown type name CUDA graph, right? Unknown type CUDA graph exec, right? So you can clearly see that some of the CUDA APIs are not migrated, right? So then we'll have to look at the code and then see if we can manually migrate some of this, right? So let's go to the source files. So if you look at the source file, the main.cpp, you can see that we are doing a bunch of memory allocations, and then the actual computation is actually executed here, right? So mainly the way this CUDA code was written was that they have 3 methods that they are actually submitting and then computing the Jacobi algorithm, right? So one is, you can see that one of the method is using Jacobi method CUDA graph exec kernels, and then there's also Jacobi method CUDA graph exec, and then there's just the Jacobi method GPU, right? So there are 3 different approaches this example has used. So mainly currently the SYCLomatic tool does not support CUDA graph migration directly, but there are other third-party libraries that are available which you can manually migrate, right? But in this example, since there are 3 different approaches, we know that the third approach here is not using CUDA graphs, and we can just execute only the third one, and then if we will, for now, we'll just ignore these 2 methods, right? So that at least we can see that at least part of the code is migrated and we can actually get the output. So these are just the 3 alternatives to compute the Jacobi algorithm. So we'll just focus on only the third method. So to do that, what we'll do is we will just comment out this section of code, right? The 2 Jacobi method CUDA graphs, we will just ignore those 2. So what we'll do is we can just delete that line. So what the code will do now is it will just use this one method to compute the Jacobi algorithm, right? And then we also have to delete the actual definition of the 2 functions that we are not using. So that functions are defined in the Jacobi CPP file here. So if you look at this code, you will see that it has the kernel code here. And if you keep scrolling, you will see that this is one of the functions that we just deleted that we are ignoring, mainly because it's using the CUDA graph APIs, and then the SYCLomatic is not migrating that specific API currently, right? So if you really want to migrate it, we'll have to use a third-party library and then migrate that. So for now, what we will do is we will just remove this function, right? So let me scroll down. So this was one of the function here. So we will go ahead and then delete that one. And then we will also delete the second function that we deleted from the main file. Right, so we deleted those 2. And then all we have is this one method, which is Jacobi method GPU. And that is what is in the main file. That is the function that's being called, right? So now, hopefully, after doing this modification, we should be able to compile this code, right? So let's go back to the terminal here, and then I will compile this again. So you can see that we didn't see the errors that we saw in the previous, right? Because we mainly removed the options that that are using CUDA calls that cannot be migrated, right? So let's go back into the file and then review the code that we have. So you can see that the main kernel code is right here under Jacobi method, and you can see that the kernel code is creating subgroups here. So this is same as the CUDA warps, and you can see that it's also using shuffle function as an example. It's also doing some atomic operations, right? So these are all CUDA source that was migrated to SYCL, and it's using the equivalent APIs that are in SYCL. So if we want to compare this with the CUDA example, so we can go back to GitHub here, go into samples, CUDA features, and Jacobi CUDA graphs. So here, if we access the Jacobi.cu, you will see that you will see a similar code pattern, right? So in CUDA, they're actually using the CG tiled partition, right? And then in SYCL, that is being changed to creating these subgroups here, right? And then CUDA, it's actually using this shuffle down, right? And then in SYCL, that's being migrated to a similar API called shuffle_down. And same thing, you look at in CUDA, there's the CUDA atomic add, right? And then in SYCL, this was migrated to the atomic fetch add, right? So these are all, for every CUDA call, there is a SYCL equivalent, and then the tool automatically has migrated all those here, right? So if you want to run this code, we just compiled it, and you can see that it's created an output file here. So we can just run this output and then see that there is an output generated. Right, you can see that there is some output being printed out. We can also run this on a GPU system. So let me log into a node which has a GPU, and we will try to run the same output on the GPU, right? So let me go into the folder. CUDA 3. Right, so we've already created an output file here, so we can run the application here, and then you can see that the GPU processing time, so it's like printing out the output here, right? It's it took 3000 milliseconds, right? So once we've migrated this code, so there are various optimizations we can do once it's migrated to SYCL, right? So usually SYCLomatic will just assist you to migrate the code, but then you still have to, check the code and then do more optimizations, right? So so after analyzing this code, so there are various optimizations you can do. If you inspect the algorithm here, you can see that what it's actually doing is, if you look at this section of code, it is mainly using a for loop, and then it's mainly shuffling. It's doing a shuffle down on the subgroup, and then at every offset, it's actually calculating the sum. So essentially, what this 4 lines of code is actually doing is it's doing a reduction on the subgroup, right? So in SYCL, there is a API directly that can be used to do this reduction operation in one man, right? So we can try to replace this piece of code and do a direct reduction as an example. So then we can check the performance, right? So let's comment out this code here. And then instead of doing shuffle within the for loop, what we will do is we will do a reduction to calculate the row thread sum, right? So there is a SYCL function called reduce over group. So you can use this. Then we specify the tile, the actual element, and then we specify what kind of operation we want to do. So we can just specify we are doing a reduction plus operator. So this is this will produce the result that same as what we used to get for the previous one, right? So this is just doing some optimization so we can save, right? And then try to compile the code again, right? So let me copy this. Okay, so you can see that the compile just finished, and let's try to run the code again. So now you can see that the previous output had 3000 milliseconds, and then now it dropped to 1200 milliseconds, right? Just with that one optimization. So you can inspect the code more because there are more of these shuffle down commands that are being used to do reduction instead of using this direct method. So we can do similar optimizations in the code here. So you can see that in the final error function, again, we have one more shuffle down here and also another shuffle down here. So what we can do is we can do the similar optimization and see if there is any performance improvement. So just comment out that code, we will paste this and then just replace the variables. 32, so this should be good. So sum, okay. And then we can also do the same thing for this code block right here. Okay, so once we've done those changes, let's try to compile and run again. Yes, I think we got slightly better performance than the previous one, but overall you can see that the original code that was generated by SYCLomatic gave us, gave us functionality, functional correctness, but then we can still further look at the code and then try to optimize, because when the migration is done, it's just migrating 1:1 as to what for every CUDA call, it's migrating to a similar SYCL call. But then if you if you look at the SYCL specification and then look at all the different group algorithms and the features that are available, you can honestly like fine tune the code to get a much better performance using SYCL. So that's mainly the example I wanted to show. So everything that I've done is actually documented right here, right? So we show clearly what should be done on the CUDA development machine, which is installing SYCLomatic and then running the SYCLomatic tool. And then once the output is generated, what we did was we analyzed the code, we compile and run the migrated SYCL code, right? So that's what we did. You can either do this on Intel Dev Cloud, like I just showed, or you can, if you have a development machine with Intel CPUs or GPUs, you can do the same thing. And the command to like compile is right here. So this is the command I was using to compile the code. And then I also explained what I did exactly to fix the unmigrated code, right? Because the first time we ran, we did see some errors. So mainly explaining the example that was used to migrate was using 3 different options to migrate. 2 of them are using some advanced CUDA features which are not being migrated. So we simply just ignore these 2 methods and then just focus on this third method, right? So basically what we did was we replaced this section of code with just these 3 lines here. And then we migrated the code, and then we analyzed the code, right? So the migrated code, once we got the output, this table just shows like what were the sections of CUDA code that was changed, right? So obviously the header, instead of using the CUDA runtime, was replaced with these 2 header files, the SYCL header file and also the DPCT header file. There was a CUDA malloc host that was migrated to malloc_host. The queue, there was CUDA stream created, right, using the CUDA stream create with flags function, and that was mainly replaced with the SYCL queue. And then we have CUDA malloc, which was replaced with malloc_device. We also have CUDA memset async, which was replaced with memset. There's CUDA memcopy, which was replaced with the memcopy command. There's CUDA free, and that is replaced with SYCL free. And in the kernel function, you can see that CUDA uses the thread block, right? And here we use the item.get group, and same thing in CUDA we use this CG sync to mainly act as a memory fence, and then in SYCL we use the barrier function, right? Same thing in CUDA, there is the tile partition, and then SYCL there is subgroups. Shuffle down is replaced with shift group left, and then atomic add in CUDA is replaced with the SYCL atomic fetch add, right? So this table just gives you a summary of what are all the different migrations that happened when you use the SYCLomatic tool, right? So this is mainly for reference, and it also shows you, the section shows you what are the optimizations we did, right? So we mainly took this piece of code here, which was mainly had a for loop, and we were doing a shuffle operation, and we replaced this entire thing with just 1 line of code using the reduce over group function. Okay. So once you do this, so we can look at any other optimizations we can do. So another optimization we can do is like see if any of the kernels can be overlapped, and based on that we can try to set up the kernels so that kernels which can overlap instead of running sequentially. So that's this document gives you a tip. And also you can do more optimizations by modifying the workgroup and subgroup sizes in the code, right? So depending on the hardware, there is limitation on what the maximum workgroup size or subgroup size can be. So based on that, you can further optimize instead of using the specified subgroups size and specified workgroup size. You can modify that to use whatever value is convenient, right? Yeah. So and finally, this document just shows you like all the source code, the original source code, where the GitHub link where this code was used, and then we migrated the code. So we have the code at every step, right? So the first DPCT output is the direct output of the tool, and then SYCL migrated is the one that we modified to get it to compile, right? So this folder will have the code for that, and then finally we have SYCL migrated optimized. So this is the code that we added some performance optimization, so that we get better performance out of it. Right, so this is the first example that I wanted to show. Let me know if you have any questions. So let me quickly check the chat. I don't see any questions. Feel free to unmute and ask any questions if you may be having. Hopefully you were able to follow this and then do it on your end as well. If not, please, this document is available on DevCloud, so you can follow the instructions and then do it at your free time. Right? So if there are no questions on this example, so there's one more example I wanted to show in today's workshop, right? Which is module 4. I will jump to that one. There are no questions. Right, so module 4, which is a SYCL migration for matrix multiplication using the CUDA library, right? So let's look at that example. So again, this document in detail shows you how to access the GitHub repo to get the CUDA source, how to install the SYCLomatic tool, migrate the code, and then compile and execute the SYCL code, right? So mainly I will go through this exercise again. So to do that, so let me jump to my CUDA development machine again. And then show you this example. So give me a few seconds here. I might have to log into this machine again. Okay, so let me go into my test folder. That's where I have the Nvidia CUDA samples. And then the next sample we will be accessing is in the folder called CUDA libraries. CD. And then inside this folder, you should see an example for matrix multiplication CUDA, right? So mainly what this example does is, you can see the source file here. It just has one source file here, and it also makes use of some helper functions, right? So this mainly, let's look up the code on GitHub, right? So you go into the fourth folder here, and then go into matrix multiplication CUDA, and then let's look at the source file, right? So mainly this example does a simple matrix multiplication using CUDA. You can see that the CUDA runtime is included, but it also includes the CUDA library, which is mainly a CUDA library to do BLAS and gem operation, right? So you will see that if you scroll through the code here, somewhere in there, you should see that this code is actually using the BLAS library, right? So the matrix multiply function is here. So let's look through this code here. you'll see that it's actually, so since you guys are experts in CUDA, you can see that it's actually using the cuBLAS SGEM function, right? So we'll try to migrate this code and see what kind of SYCL code is generated by SYCLomatic, right? So let me switch back to my CUDA machine here. So I'm in the matrix multiplication cuBLAS directory. And I will migrate the code. So let's do C2S. First step is you would do intercept build and then make. And this should generate the compile commands file, right? So once that is generated, so we'll run the SYCLomatic tool. We can specify -b, and then we can specify the JSON file. And then we will also specify the path where the common files are, which are 3 directories behind, so right at this spot here. And then we need to add this other option to copy the header files. So let me copy that command. So mainly this document has all the command lines that we are using. So if you add this command, use custom helper, so this will make a copy of the header files, SYCLomatic header files that are used to generate the code. Right. So if you run this code, you'll see again a bunch of warnings, and then if you look at the directory, it would have created a folder called dpct output. So if you go into dpct output, again, you'll see that the common files are copied over here. The include files from SYCLomatic are copied here, and the sample migrated files will be in the samples folder. So if we go into samples, matrix multiplication, you will see that instead of the CUDA file, it's now generated the C++ file, right? So if you look at the C++ file, you should see that all the CUDA APIs will be converted into SYCL APIs. So at the very top, you can see that the CUDA header file is replaced with these 2 header files, SYCL header file, and then the SYCLomatic header file. So let's scroll down and inspect other lines of code here. You can see that it's getting the GPU device name. So these are all used to be like CUDA APIs. Now it's being all migrated to SYCL calls. And again, here you can see in the original source, it was using CUDA malloc function. Now it's using the malloc_device function, right? So the next step is, since we have the C++ SYCL source created, so we will have to copy this source from your CUDA machine into your dev cloud or your machine which has one API compiler installed, right? So what we will do, again, like in the previous case, is we will move to the Intel Dev Cloud and then try to compile the migrated code, right? So I will jump into Intel Dev Cloud again. So this document has all the instructions that we just did. So we completed until migration was done. We ran this command and then we got the migrated source file. So the next step is mainly we will analyze the code and then see whether we can compile the migrated code, right? So let's look at, so this same folder should have the dpct output already copied. So you can either use this copy here, or you can manually copy the files from your CUDA machine into Dev Cloud and then compile those files, right? So if you go into the samples matrix multiplication folder, you'll see that there is one source file, CPP file. Let's look at the source file here. Like I showed you earlier, you can see that the CUDA header files have been replaced with SYCL header files and then DPCG header file, which is mainly the tool header support files. And then if you look at the code, initialize CUDA. So it mainly leaves the function name as it is, what's in the CUDA source, but the actual CUDA APIs is what is migrated, right? So if you want to clean up the code, you might have to, if you think this is not relevant to just CUDA, actually you can start renaming these functions as well. So let's look at the matrix multiply function, right? So here you can see that we're doing memory allocation, we're doing device allocation here, and then we copy the memory, which is mainly matrix A and matrix B are being copied from host to device memory, right? And then we also create an allocation for matrix C, right? And then we are creating the thread and the number of threads and then the total grid, right? So this is same as work group and then the global range of in SYCL, right? Which is what is used when we are doing the actual computation. So in here, you can, if you go through the code here, you can see that the actual foo_blast function is actually replaced with the MKL blast function, right? So the MKL column major gem function. So this is the SYCL code. So this is the main migration that was done by the tool, right? So if you look at the CUDA code here, you can see that we had a foo_blast sgem function, and that was after migration, it was replaced with one API MKL blast gem function. Right, and then it computes the output, and then we copy back the result, and then verify the results. So that's all this example is doing. The example itself is very simple, but the difference between this example and others is that it's actually using the foo_blast library, which was replaced with the MKL library. Right, so now that we have the source code, we can try to compile this one. Right, so I'm in command line again. So let me go back to 04 folder, the fourth module, which is the matrix multiplication foo_blast folder. And under this one, we have the DPCG output. And under this folder, we have samples, matrix multiplication folder, and then here we have the actual source file. So we can compile this code using ICPX compiler. So all you have to do is like do ICPX minus F SYCL. And then we will include the common file. We will also include the SYCLomatic helper files, which is in the include folder. And then finally, we specify the actual application file, which is matrix multiplication foo_blast.cpp. We'll ignore all the warnings and then see whether this one will compile. Okay, so we are seeing some linker error. No, it's mainly saying MKL is undefined. So I think we have to use some other command line options here. So let me go back to and copy the actual command. So you can see that we have to use some MKL SYCL flags to compile this. So let's compile this again using the MKL flags. Hopefully this should compile and not give us any linker error. So you can see that the compile just finished. So I think the issue was that we didn't specify these flags, MKL flags to compile. So now that this is compiled, you can see that there's a a.out created. So we can run this file, and then you should see the matrix multiplication output and verification. So you can see that it's just showing the verification was done, and then we tried, I think, 3 different matrices of different sizes, and then it shows you the time it took. And the result is a pass. Right? Okay, so let me know if you have any questions. So this was the second example, mainly that I wanted to show in today's session. Okay, so we have a question from Alfred. Can I use any C++ compiler for the files generated by C2S, or am I limited to use ICPX? Yeah, so ICPX is mainly the Intel optimized compiler, right? So you can also use CLang++ to compile, so that will also work. But the main reason we are using ICPX is because it also includes the SYCL. It's also a SYCL compiler, right? So if you just use C++ compiler, so you will get the errors, right? So we can try this. I can show you, let's say, let me show you this very simple example, right? So the very first test example that we did. So one way to compile is ICPX SYCL and test.cpp. So there are some errors, so you just ignore the errors and then compile again. So you can see that when we are compiling this test file, we are actually using the SYCL flag. So that's why it's able to compile. So we have the output here, right? But if you just use a C compiler, it will actually throw some errors, right? Because it doesn't know what SYCL or HVP is. So if you're using any C++ compiler, so you might run into this error, right? So the other way is like you can build the open source LLVM compiler, right? So that instead of using ICPX, you can also use the CLang ++. Again, even for this, right? So you still have to use that SYCL flag. So both will work. The main difference between ICPX and CLang is that ICPX is Intel optimized for the CPU. And I think the question is, what is the W flag? So that's mainly to ignore these warnings, right? So remember the first time I compiled without W, it ended up generating all these warnings saying, so yeah, just using W will actually just ignore these warnings and only give us if there's actual errors. Okay. Okay, so with that, so that's all I had for today's session, these two examples. So let me quickly go over some of the things that we did, right? So in case people want to try this at home on their own time, if you go into this introduction document, so there's this section for tips for migrating CUDA to SYCL. So again, sanity check, just make sure that your CUDA development machine is in the right working condition. By running Nvidia SMI, check that your CUDA include files are in the default path, right? And then just make sure that NVCC is working. So this will make sure that your CUDA development machine is in a good state, right? And then next step is installing SYCLomatic. We have instruction for that. Here's the link to get the releases, and then we copy and then unzip it to a folder, set the export the path to make it easy. And then the tool usage, right? So we saw like the very first example, the way we migrate is just C to S and then the CUDA file, right? And there are these different options. If you want to copy all the header files, the helper header files, then you will be using one of this option here. If you, by default, it creates an output folder called dpct_output. But if you want to create a custom output directory, then you can use this option here, use out root, and then specify any folder name you want, right? And then we also use this in root option. This is mainly to specify where all your support files are, so that it doesn't just migrate test.cu, but also looks through all the support files that it's used and then migrates all the files. Three, so we looked at that one. And then, so this is important, right? So we talked about this one. So in case you haven't installed your CUDA in the default installation path, which is user local CUDA, right? Then while running the tool, you will see some errors. So if you have installed CUDA in a different path, then you have to use this CUDA include path command line option, and then specify wherever you have the include files. So these are the CUDA header files, right? So you'll be using that. And finally, if you have larger projects, which has a make file, then this step is actually showing how to migrate when you have a make file. Use intercept code make, which generates the JSON file, and then just run this C2S with the JSON file that will migrate all the files. Right? So you can use any combination of these command line options. So these are just the most commonly used command line tool options. If you use C2S --help, it shows you all the different experimental features that are there, or different coding style you want for the output, and you can set all those options. And there is a quick instruction on how to compile the SYCL code, right? So if you're using the Intel Dev Cloud, you just have to log in, because we have all the compiler tools installed, so you can just compile the code. But if you want to install it on your own machine, so there is a link to installation guide, so we can install the Intel One API based toolkit, and also the plugin, and then you will be able to compile. So mainly you have to set the environment variable, and then we are showing how to compile for Intel CPUs, as well as for if you want to compile for Nvidia GPUs. All right, and you can compile it for Nvidia or AMD. This is just showing how to set Nvidia target. Right? So this is just a quick guide for you to understand how the migration works, and then how to compile. Right? And then finally, we have program structure of the migrated SYCL code, right? So the migrated SYCL code, you will notice that it will have a new header file called dpct/dpct.hpp. So this is mainly helper files. This is mainly wrapper for actual SYCL functions, so just to make it easy for to do the migration. And all these header files will be added to your output folder as long as you have this option specified, right? And then you would, it's just showing how the code is being generated. So usually when the SYCLomatic generates the code, it uses the DPCT wrapper to make the actual SYCL calls. So if you want to understand what's really behind the actual SYCL call, you can look at the header file, and then you'll notice that under the hood, it's just making SYCL calls. Okay. So hopefully this introduction documentation should be helpful for you to get started. And then once you're done with that, for now we have these 4 examples, starting with a very simple one. Second example, we just have a lot of CUDA files, larger project. Jacobi Iterative, the third one we just did today, which uses a lot of CUDA APIs, like CUDA hardware APIs, and we migrated that. And the fourth one is mainly using a CUDA library that we migrated, which migrates using the MKL library, right? So we have these 4 examples. So eventually we will be adding more and more examples. That is helpful for migration. So keep on the lookout. So we will have this constantly updated. So if you update it the next time, you might see more modules in here. So with that, we are done with today's session. So we will continue again next month. I think it's April 12th. So that session will mainly be if any of you are working on any CUDA code and planning to migrate, or if you're in the migration process. So this is mainly the next month's session is mainly time for you to share. And then if there's any code that needs to be debugged, if you're running into any issues, we can look at that. It's more of a Q&A session. And if there's not much code that anybody wants to share, so we can always use the time to show you more examples on how to migrate from CUDA to SYCL. So yeah, please keep that in mind, and yeah, go through the introduction document, and then if there's any project you're working on, please go ahead and try it. And next month we can actually review that code and then use it more as a working session for this migration. Yeah. So that's all I had, Ray. If there is no more questions, I think we are done with today's session.